Good morning, guys. Welcome to Modern Physics 2. Spring 2020. We're in the chapter on atomic structure. This is chapter 9. This is part 6 for the fifth time that I've tried to record this video. Anyway, just having some storage issues on my iPad here, and I'm hoping that I'm going to do this in 15-minute chunks, hoping that I can upload those with the audio and not have any further problems. So in this discussion, we're going to be talking about electron spin. And I want you to recall that when we looked at the hydrogen atom, from that theory, we got three quantum numbers, n, l, and m sub l. In this chapter, we discussed how m sub l was responsible for generating a orbital magnetic moment, right? An orbital magnetic moment. And then that gave rise to the prediction of splittings in the absorption and emission spectra of hydrogen. And that was called the normal Zeeman effect. Now, the normal Zeeman effect is not typically seen, but surprisingly, the absorption and emission lines are still split. And that confounded physicists at that time and got them to think about other magnetic moments that could split the emission and absorption lines in the presence of an external magnetic field. So if we just quickly review, we looked at the orbital motion of an electron, and that gave rise to an orbital angular momentum L, an orbital angular momentum, and because of the negative charge on the electron, that gave rise to an orbital magnetic moment. Okay. Now, what was being toyed around? What was being toyed with at that time was that the electron itself could very well be rotating about some axis. And the electron now being negatively charged, being a charged entity, one could imagine that we have these infinitesimally narrow annuli, each being made up of some small chunk of charge delta Q. By virtue of rotating around that axis, that would give rise to a current, and then that would give rise to a magnetic moment. So in this particular case, however, that magnetic moment is due to the spin of the electron. And again, I want to put in quotes spin, because I also want to, from the very beginning here, say that there's no evidence that the electron is actually spinning about any axis. So from here, we're going to strictly move by mathematical analogy. And the analogy is going to come from what we already know from the orbital angular momentum. And so the orbital magnetic moment is equal to negative E over 2 m of E times L. And so it was thought that one can use the same mathematics, and that this spin magnetic moment now is going to be equal to negative E over 2 m of E times this intrinsic spin angular momentum. L now, right, being the orbital angular momentum. So this looks all well and good, but the electron is actually a peculiar beast, and actually its charge to mass ratio is not uniform. And a consequence of that is that the relationship between the magnetic moment and the spin then needs to be modified. And so it's modified by a factor, G, which is called the G factor. Imagine that. And so the G factor for the electron is usually given a subscript G sub E. And so then this is just called the G factor for the electron. And the G factor for the electron is one of the best known physical constants. As a matter of fact, G sub E is equal to 2.0023 193.0456. And that's an experimentally determined value. Surprisingly, however, that value can be theoretically determined using quantum electrodynamics. And the correlation between the theoretically determined and the experimentally determined values is incredibly good. And so it really validates quantum electrodynamics. So I'm going to end right there and see if I can upload this onto YouTube with a video and with a complete set of notes. And then I will pick it up from here. So awesome, guys. All right, have a good morning.